So in this video, we're going to learn how to calculate arc length. So what is arc length? So imagine we had a plane flying on this path in purple. The arc length is basically just the measure of the total distance the plane traveled from, say, maybe this point, and the plane would go and it would dive, and maybe until this point. So we could measure the pure total distance that that plane traveled on from this point to this point. That's what arc length is. It is simply the total length of some curve. So if I took that red line, if I imagine that red sort of curve, that red portion was string, if I took it out and unraveled it into one single length, the arc length would just be that total length there. You can measure it with a ruler. But in this video, we're going to learn how you can use an integral to measure this total length. And that's important stuff because, if I'm the pilot of that plane, I start here and I'm traveling, and I go on a dive, and I'm going and going and going, and at that point I say, alright, what is the total sort of distance that I've traveled? I'll carry out this integral, and if my math tells me, oh, you've traveled 105 meters, that might be important. I might be able to use that in fuel calculations to say that, oh, I only have maybe, 2 gallons of fuel left, or, something like that. So what we're going to do is we're going to build up an approach, a method, on how we use an integral to calculate the total arc length, say from maybe here all the way to here. Much like we built up the disks approach or the cylindrical shells approach for volume calculation. So if I wanted to calculate the total length of my curve from, say, from here to here, how would I do that? Well, I could use distance formula. This is my final point. This is my initial point, which makes delta x this length, delta y this length, and my distance between these 2 points would be that hypotenuse. My delta s is what I'm calling that distance. And just know that the distance formula is just Pythagorean theorem. We have our a squared plus b squared is equal to c squared. Just in case you didn't know that. Now, if I use the distance formula to calculate the distance between those 2 points, that is not the exact length of my curve between that initial point here and that final point here. But it is close. What we can do is we can break up that arc of the curve into several little distances and use the distance formula to calculate the length of each one, and then simply add up all these little lengths. And you can see that we get even more accurate in estimating the length of the curve from here to here. Now I can keep going with that idea. I can keep making each one of these little distances smaller and smaller and smaller, such that there are even more and more and more of them along this length. And when I make each one of these distances very, very small, what that does is it makes my delta x become a dx and my delta y become a dy. Remember, dx and dy are the same as delta x and delta y. It's just that they are what we call infinitesimally small, differentially small. It's just microscopically small, and you can keep getting smaller and smaller even after that. So at this point, I'm using this form of the distance equation. And at that point, what we would like to do is we would like to add up all of these little distances from this initial point here to this final point here. That would make sense to calculate this total arc length. And my integral would look like this. There's only one problem though. We know what integrals are supposed to look like. They're supposed to look like this. Some function of x being right here, like x squared or sine of x or something, times a dx here. Or an integral with respect to y would be the integral of some function of y times dy. Notice how we don't have that here. I need to either get a dx out here or a dy out here. This is not a valid integral yet, but we can make it so. Watch this. All this talk of making, of zooming into a point and making the distance really, really small, all this talk makes me think of my derivative. Remember, the derivative of whatever this equation is will give me that instantaneous rate of change, that tangent line slope. I mean, if this equation was negative x squared, let's just say it is, the derivative of it would be negative 2x. And that would be this guy. So with that being said, why don't I multiply both sides of this equation by dx, which in effect moves that dx to the right-hand side. Now with this, I can plug this dy into the dy here. We definitely cannot have dx and dy both in the same integral expression. It's either got to be dx or it's got to be dy. So I'm going to try to eliminate dy, replace it, using our derivative idea. So there it is, right here. So now, let's just apply some algebra. Let's take that squared and apply it to both the derivative and the dx. And now we notice that we have a common factor. Dx squared is here and here. So let's factor it out. And now, because I have two different terms separated by multiplication here, all underneath the radical, I can apply that radical to both of them individually. What that does is it turns the dx squared into just a dx. So now I have an expression that gives me ds, the length of one of these tiny distances. And also know that I've put it into a nice integral form. I have some function here, some equation that depends on x, and here I have my differential x. So now if I wanted to, I could add up all of these little distances, ds, starting from some x initial ending at some x final. There we go. So let's just say we were applying it to the graph that we see in front of us, the negative x squared. Let's just pretend it was negative x squared. I know it doesn't look like it. I would want to add up all of these little distances ds. Starting at this one right here, well, what's the x-coordinate of that starting point? Well, that's going to be x is equal to, x is equal to 2, 3, 4, 5, 6, 7. So our ending point is here. The x-coordinate of that guy is 7. Alright, got my bounds. Now for this, all this is the derivative of this equation with respect to x. It's simply going to be negative 2x. So I would just write negative 2x, all of it squared. And that would be my setup for calculating the length of this curve from here to here. Now, sometimes a curve is not given in terms of x. Sometimes it's given in terms of y. So maybe this curve is given as an equation of y, and the name of the equation is g. And let's just give it a concrete example. Maybe x is equal to y cubed, let's just say. So I couldn't use this integral that we built, because if I was to take the derivative of this thing, it would be dx over dy. It would be 3y squared. That derivative would be a function of y, g prime of y, you might say. Well, in our form of the integral down here that we built, this derivative is the derivative with respect to x. So what are we supposed to do if our curve is given to us in the form of a y equation, x as a function of y? Well, going back to our stage here, if you remember, what we did was basically eliminate this dy, because we know that an integral must be a dx integral or a dy integral. So we made it a dx integral by focusing on getting that y out of there. Well, we can do the opposite now. Let's try to get dx out of here and make our integral a y integral, a dy integral. Well, we can do that. If we're given an equation in terms of y, the derivative of that equation will be dx over dy. Dx will be the rise, dy will be the run. And this derivative will be as a function of y, just like we're seeing in our concrete example. It will be in terms of y. Of course, if we want to get the dx removed from our main equation right here, I can get dx by itself, and now I can take this dx, and plug it in for this one. Notice how my dx is out of there. I just have dy's now, which is good. So, with my expression here now, I can basically perform the exact same algebra steps that I did on my left side. And what we get as a result of all that is this. Remember, all this is a way for us to calculate a tiny bit of one of these distances, but this time in terms of y. And of course, my final step is I want to add up all of these little distances, which I can do now because I have a valid integral. I have some function of y, that's this, times a dy. There we go. So applying it to our concrete example, let's do our bounds. Here's my point where the first little ds will be. Okay, what's the y coordinate of that point? 1, 2, 3. So y initial will be 3. That's our starting bounds. Our ending bounds will be here. What's that y coordinate? That'll be y is equal to 5. And what is the derivative of this curve in terms of y? That's just 3y squared. So this right here, my integral is finally built, and all I have to do is crunch the math. So, just to recap, the entire purpose of this section is to calculate the length of some curve from some initial point to some final point. And the way we approached that was adding up all of these little distances. Well, how do we form these distances? By using the distance formula. We made each one of these distances so small that the delta x becomes a dx and the delta y becomes a dy. So this is how we calculate one of those little distances. But I can't use the integral on this guy right away because we know what a proper integral looks like. So from that point, we could either eliminate the dy and make this whole ds be in terms of x, that was our work on the left, or we could work to eliminate the dx and make our whole ds be in terms of dy. That was our work on the right. So for curves given in terms of y, of course you'll want to use this form. And if your curve is given in terms of x, like in the very beginning example, you would use this form. And sometimes you have to choose yourself which form to use. Let's say this curve was y is equal to radical x, and they want us to figure out the arc length from some initial point to some final point. So we'd be using that dx form of the integral, so the bottom left, which means we would need to calculate the derivative of this curve in terms of x. Well, that's no problem. Performing that power rule, we would get this is our derivative. Alright, so we would throw that into our integral. And what we would get would be this. Of course, we could apply that square to the derivative, and we would get this. So, long story short, none of the integration techniques we learned, trig sub, partial fraction decomposition, integration by parts, none of those would work to perform this integral. So at this point, you would choose to say, okay, let me try attacking this problem with the dy form of the integral. So you would need this same curve, but you would need it in terms of y. So you would square both sides, and you would get x is equal to y squared. Going with my dy form of the integral, I would need to calculate the derivative of this curve in terms of y. Well, that's no problem. It's even easier than last time. Dx over dy is equal to 2y. Okay, so we would take this and throw it into our derivative with respect to y. And we would get this. And of course that squared would turn that 2y into 4y squared. Now, to perform this integral, you could apply the trig substitution method. This one would actually be doable, while this one, the x form of it, was just impossible. So just know you can use either or approach, either or form, to figure out the arc length. But sometimes one way will be easier than another way. So just keep your mind open to that. Okay, well that's arc length for you. If you want some practice using these two approaches to calculating arc length, I'll have a video that works out some practice problems.